unlikely that it's going to be very, very rare cases in the history of science where it's genuinely a philosophical idea that requires a breakthrough. And physicists are not bad at thinking through philosophical ideas that are directly relevant to their areas. Physicists have worked out a good understanding, I think, of things like the anthropic reasoning, explanations of kind of naturalness in terms of naturalness um, of parameter values.
The guest of today's podcast is Dr. Alastair Wilson. He is a philosopher at University of Leeds who works on metaphysics, epistemology, philosophy of science, and philosophy of physics. His doctoral thesis was on the metaphysics of Everettian interpretation. So let's welcome Dr. Alastair Wilson on the podcast and listen to what he has to say. Dr. Wilson, welcome to the podcast. Nice to have you.
Well, thanks. Thank you for the invitation.
So you wrote your doctoral dissertation on the Everettian interpretation of quantum mechanics, and there are some people out there who are like the proponents of this particular interpretation. So although I'm pretty sure that most of the people in this audience are familiar with what this interpretation is, but if you had to give like a quick description of what this interpretation is, how would you put it?
Well, I mean, it's a huge field because there are many, many different approaches to the many worlds and to Everett. One of them is many worlds. Perhaps the most common approach is to think of it in terms of many worlds. The basic idea that people take from Everett is the no collapse idea. It's the idea that essentially collapses are a problem for understanding quantum theory in a realistic way that tells us what the world is like. And so we should just see what happens if we don't have collapses in our theory. And then we just have quantum theory with unitary evolution. And we try to understand what a world like that would be like if there were no collapses. And one way of imagining what a world like that would be like presents it in terms of many worlds. That wasn't really part of Everett's own original way of thinking about it. He kind of used diagrams that divide reality into these kind of branching streams. He didn't use the talk of many worlds. He preferred to talk about relative states. The modern version, or rather the kind of version that I've worked with for most of my career, is a many worlds version of Everett's interpretation, but it's a version of many worlds where the many worlds are taken to be emergent entities rather than kind of part of the fundamental ingredients of the universe. I think that's compatible with Everett's writings. There's nothing inconsistent there. Whether he would have endorsed it is a further question, but it's been defended by a lot of modern Everettians in philosophy, in particular Simon Saunders and David Wallace. Latley, Hilary Graves, some of these sorts of people have developed a version that uses decoherence to define a structure of emergent worlds. So it is a realist theory. It says there are many worlds, different outcomes occur in each, there's a probability distribution over them, and it's quite a rich theory. There's lots of different aspects of it that are philosophically interesting, that have caused no end of interest in philosophy of physics over the last few years.
I see. So apart from the question that, are these worlds emergent or not, are there some other points on which different defenders of many worlds disagree on?
Yeah, I mean, it's sometimes said that there are kind of as many different versions of the many worlds interpretation as there are theorists interested in the many worlds interpretation. Kind of everybody that endorses it endorses their own particular kind of spin on it or their own particular variety of it. So there's a sort of family of theories rather than one unified theory. I mean, one of the things that disagree on is whether we should think of it in terms of many worlds at all, or whether we should think of it as one world that has some unusual features. So the basic choice is between many worlds where each of the worlds kind of approximately looks like a classical universe. and instead a picture where you have just one world, but that one world is kind of radically non-classical and quantum, and in some sense contains all the different possibilities somehow within it. And then there are lots of different ways of understanding that. Quite a common way of understanding that is to talk in terms of relative states. So that there's one world, but objects within the world have their states relative to the states of other objects. There's no such thing as kind of the unconditional state of a thing, except perhaps the unconditional state of the universe as a whole. There's only relative states. And that lets you kind of stay close to common sense in the sense there's still only one world, but you end up having to go further than common sense, further away from common sense with regards to what that world is like. So the many worlds approaches, depart more from common sense in that they say there's many worlds, not just one, but then they get to stay closer to common sense in that what they say about each individual world is closer to the classical picture. They're not completely classical, obviously, but in their basic type, each world in a many worlds picture has definite macroscopic events in them that happen one way and not the other way, and they're not relative to anything new. It's just kind of more of the same on the many worlds picture.
I see. So when you say that there is a single world, do you mean that there is a single wave function and there is a single Hilbert space for all the world?
Yeah, you say that kind of is properly called the universe or the physical world or physical existence. So I'm using the way the word world gets used in philosophy of physics here is a little bit of a mashup of the way it's used in physics and the way it's used in philosophy. So there is this kind of widespread use of the term possible world in philosophy, where a possible world is the whole totality of everything. And so the usual way philosophers would think about the many worlds interpretation is that it describes a possible way physical reality could be, but that all those different branches of the wave function still exist in one physically possible world in the philosopher's terminology. Because for a lot of philosophers, world is defined to mean kind of everything that exists. But in philosophy, everything gets disputed, including what we should mean by the word world. And in fact, in my own work, I've argued for a different way of thinking about it, whereby possibility and existence are related a little bit differently, so that other possible worlds could still be real physical existence. But perhaps we'll talk about that a little bit down the line.
Sure. So would it be accurate to say that different worlds are like different sectors of the Hilbert space, or would that be not correct to say?
Yeah. So as I talked about in the modern many worlds interpretation, that would, I think, be right. I mean, what is important to them being worlds is that they be in a certain sense separated off from one another. In particular, that they be in a certain sense causally separated off, causally isolated. So it's an approximate kind of causal isolation. But it's sort of definitional of the world in the many worlds interpretation that you can't throw a ball in one world and break a universe and break a window in another world. They're separated from one another. The cause and the effect kind of happen within them. So you have within a world, the throwing the ball and the breaking of the window, it's all locked into that world. Of course, there is the question about how we understand quantum interference. Is this sort of worlds literally overlapping with one another? And again, that's another point to come back to your earlier question about which different proponents of the many world interpretation will disagree. Some will say that the worlds literally do overlap one another, and they kind of share segments. So it's like the trunk of a tree. If the tree grows up, it has a single trunk, and then it splits into multiple branches. And there are sort of complete roots from the bottom of the tree up to the tip of a leaf. But that trunk is kind of common to all of those roots. Each of them passes through the same trunk. And so that's a kind of overlapping idea. All of the histories overlap at the beginning. A different way of thinking about it has them spatio-temporally separate from one another. So not just causally isolated, but kind of living in their own separate space-times as well. This is more of a parallel worlds reading of the view. So you can contrast sort of splitting worlds, readings of many worlds, with parallel worlds readings. And I think both kind of get used in the literature, both get used in kind of science fiction representations of the many worlds interpretation. But for a kind of sort of literal-minded realist philosopher, there should be an answer to that question. Kind of, are the worlds parallel, or do they split? Does the number of worlds increase over time? And that's a kind of open question that people like me argue about.
So how to make sense of, so suppose that if there is a measurement that you can do and there are two outcomes to that measurement, and the outcome of, the probability of one outcome is like 3/4, the other one is 1/4. But in many Bayes interpretation, both of those possibilities take place. So how do you make sense of probability in this whole, model?
Yeah, so probability has been one of the biggest sort of points of trouble for the many worlds interpretation. There's really sorts of two kind of main difficulties that the interpretation encounters. One is in making sense of the ontology. Does it make sense for there to be many worlds? What are the worlds like? What are they made of? Can we really get a picture where they are causally isolated properly from one another? All those questions are about what the worlds are like, the ontology. But even if you were to get that sorted out, there's a whole separate set of questions about probability, because it's not enough to just give a set of worlds to account for physics. We need to account for the statistics of measurement outcomes. And so, we want it to be that quantum mechanics makes predictions, that it predicts facts about the statistical distribution of measurement outcomes. So we need to make sense of those sorts of predictions. Those are the kind of evidence we have for quantum theory in the first place. So we need to a picture where probabilistic reasoning makes sense. And broadly speaking, the way probability enters into many worlds is as a real physical quantity that is interestingly different from other real physical quantities, but it's real and physical nonetheless. It's we think of it, Everettians kind of think of probability as a feature of physical reality. Some worlds have more of it than others, or some sets of worlds have more of it than other sets of worlds. So if the measurement, if the setup is one of uneven probability, spin up is more probable than spin down, then the worlds which are spin up worlds collectively have more probability than the worlds which are spin down. So probability is something like a kind of physical quantity possessed by collections of worlds. And it's something which enters into the laws specify its value. So that's quite a different account of probability from, I think, traditional approaches. It's perhaps easy to kind of forget that probability in physics was regarded as a kind of very mysterious and problematic, even in a one-world setting until quite recently. I mean, classical physics is deterministic. There's no consensus about how to understand classical probabilities. There still isn't any good consensus about how to understand the probabilities of classical statistical mechanics, for example. Where do they really come from? And so we'd kind of have had time to get used to probability in a one-world setting, whereas probability in a many-world setting is less familiar. But you can ask kind of questions like, why should I set my degrees of belief to particular values anyway? What's the difference kind of between a fair coin and a biased coin that means it kind of you shouldn't bet at fair odds on a biased coin? What is it about the world that fixes what we ought to do? And it's a kind of old philosophical problem of inferring the future from the past, sometimes called the problem of induction or Hume's problem. And if there's a kind of consensus on anything in philosophy, it's that you can't, it's not, there's no argument that you're kind of rationally compelled to believe that the future will resemble the past. There's always a logical possibility that things will just start to go differently, that this coin that is you think is biased against you will just kind of give a continuous set of outcomes in your favor from now on. So I think there's no good understanding of how it could be that probability could really constrain our degrees of belief anyway, even in the one world setting. So the fact that it's kind of hard to see how that would work in the many world setting shouldn't be taken as decisive. And yeah, so my own work has been in the sort of direction of arguing for parity, that people that believe in the many worlds are in just as good a position to account for probability as people that believe in a single world. And that is that, it still remains puzzling. It may be that there isn't going to be any kind of argument that we're rationally compelled to adopt the Born rule in a many world setting. It's just that kind of experience has shown us that things work better if you do.
Right.
And so we should continue to do that.
Sure.
So it's not clear that even if you can't solve all the mysteries of probability, maybe that's because some of them are kind of intractable philosophical problems, not because there's anything specially problematic about the many world setting.
I see. So I'm happy that you have gone into a bit of detail of this, of the concept of probability, because I wanted to, go in the depth of this particular concept. So a lot of people, as you surely know, use the concept of probability in the frequentist sense, where you say that, okay, the probability of a particular outcome is, number of favorable outcomes divided by the number of total outcomes. So, and most people to just use this particular definition without a second thought. So what is wrong with this definition in a very naive sense?
Right. I mean, so there are, I think there are probably quite a lot of things wrong with frequentism from a philosophical point of view, but I want to emphasize that none of what I'm going to say about it kind of means that the link between probabilities and frequencies isn't generally in good standing. So, like, generally, in most settings, reasoning about frequencies can serve as a very effective proxy for reasoning about probabilities. And any theory of probability should explain how that is. So it's not that we need to change our practice or that there's something kind of confused in what we're doing, but it's that like a full account of probability should explain why what we do with frequencies works so well. And it looks like that's a problem in the many world setting, because there are going to be lots and lots and lots of worlds that do have very exotic outcomes, very like peculiar an unlike we would think of it intuitively as unlikely combinations of outcomes, and we kind of don't want to count worlds like that as highly as we want to count worlds with very probable series of outcomes. So we don't want to just use something like frequency reasoning about worlds. If we do, we get the wrong answer. So think of it this way: if you have a balanced quantum coin that's like 50% spin up, 50% spin down, and you observe it, it should be that for a many worlds person, there's the spin up outcomes and the spin down outcomes, and they should have equal probability. For simplification, we can pretend that there's one spin up outcome and one spin down outcome. And if you just apply the basic frequency reasoning, that kind of seems okay for the case of a fair quantum coin. But then you make some further irrelevant observation in one of the branches, but not in the other. So, like if the quantum coin lands spin up, let's say, then you make a further irrelevant observation of something else and split the universe in two. And now there are three outcomes because you didn't split the universe on the other one. So now there's two spin up outcomes and one spin down outcome. Suppose you don't actually check the outcome of the coin in between. Should you now think it's 2/3 likely that the outcome was spin up because there's two spin up worlds and one spin down world? The probabilities become kind of unstable if you can kind of affect them just by kind of creating irrelevant extra splitting of the world. And so we need a rule that isn't just world counting. I mean, there are further problems with world counting. To go back to the ontology problem, there's a real question about whether it makes sense to compare just pure numbers of worlds as opposed to comparing like sets of worlds with certain amplitudes. If you try to talk about numbers of worlds, it's not clear that the emergent account of worlds that you get out of decoherence really supports a determinate number anyway. But even if you did have an account of like number of worlds that made sense, they wouldn't line up with the probabilities that you want. So at the very least, we can't get probabilities in the many worlds just out of counting worlds. We can't get the probability of spin up being the proportion of worlds that are spin up. Mm-hmm. That's where we need this real physical quantity, the measure, or sometimes it has lots of names. It's the squared amplitudes of the relevant components of the wave function, and that is part of the structure of reality according to the many worlds interpretation. It's a real physical measure. It's a real physical quantity associated with each set of worlds, and it's the hypothesis is just that is what probability is.
I see. So are you when cosmologists study something called inflation, right, which is a mechanism for giving this expansion to the universe, they don't know of a mechanism by which it can stop, so they talk about eternal inflation, and it gives rise to something called multiverses, right, in cosmology. Now there is a problem in the study of the multiverses, and the problem is as follows: that if you want to calculate the probability that a particular universe in this multiverse will have a particular probability or will have a particular property, it turns out that the number of the total universes and the number of universes with that property are both infinite. So you can't use just it will be like infinite over infinite. It's called the measure problem sometimes. So do you face a similar problem in many worlds interpretation?
Yeah, no, good question. So it really I think depends on a lot of hard questions about that we don't really know the answers to. In particular, it depends on some unresolved questions in quantum gravity, um, uh, and principles like the holographic principle in particular, to do with what exact the wave function of the universe is like, and how much physical information is encoded in any given region. So it might be that kind of if a finite amount of information is encoded in finite regions, then you only need kind of branching into finite numbers of worlds, obviously a very large finite number of worlds, but nonetheless into a finite number to model kind of local macroscopic emergent worlds. But that is kind of this question is very much above my pay grade. But one of the interesting features, I think, of philosophy of quantum theory is that we can't kind of come up with conclusive answers at the moment, because so much of them depend on the future progress of quantum gravity. Like, in some sense, it's a bit of a kind of foolish errand to try to interpret non-relativistic quantum theory kind of as a standalone theory, because we know that non-relativistic quantum theory is false. David Wallace has said some similar things. So at most, it's a sort of kind of intellectual curiosity to answer the question, what would it be like if non-relativistic quantum mechanics were correct? But we shouldn't assume that we can extrapolate easily or really at all, I think, from what we think would be the case if that were the correct physics to what actually is the case in our universe. So whether or not there's a kind of infinity problem with probabilistic reasoning in the many worlds interpretation, I think is just kind of up for grabs. It's really kind of, I think, the question of kind of what the quantum theory of gravity will look like, and what the probabilities will be like in that. The kind of in relation to internal inflation, and I think this is an incredibly interesting set of questions. How eternal inflation looks is obviously going to be different depending on whether a many worlds theory of quantum theory is correct. Because the relaxation of the inflaton field is meant to be a quantum mechanical process. In a many worlds setting, we would presumably expect that kind of all possible ways for it to relax occur and all possible ways for it to exit that occur. So if we do get a kind of multiverse of the inflationary eternal inflation kind with bubble universes, we'll get a different multiverse of bubble universes in every branch of the many worlds interpretation. So there'll be kind of multiverses layered on multiverses then. Each individual world of the many worlds interpretation will have a different set of inflationary bubble universes inside it. If you wanted to use a multiverse to sort of explain fine-tuning of initial conditions, that's a bit of a peculiar situation, because it kind of looks like you have got a multiverse twice over now. You've got the multiverse of the many worlds interpretation, you've also got the multiverse of internal inflation, and they kind of layer on top of each other. You might have thought you only needed kind of one multiverse to account for fine-tuning, and here you've got these two nested multiverses. But I think, these theories remain quite fluid as I understand them. And I don't think it's impossible that we'll in the end come up with a picture where we don't have multiverses nested inside, if perhaps there is some way found of kind of closing inflation off cleanly.
Okay.
And this is just, as I say, is outside my pay grade.
Mm-hmm.
But I think it's really interesting to kind of think about how these different possible evolutions of the entire cosmos interact with the many worlds interpretation. And at least at a first pass, it seems like we would have quantum worlds for each possible evolution of the entire cosmos, including each possible way the whole cosmological inflationary multiverse could turn out.
I see. So we have talked about probabilities, a few minutes earlier. I want to dig a bit deeper into that concept because you have done work on something called objective probability, or the probability is objective or not. So my question to you is that is probability objective, or is it a subjective thing that we use to update our beliefs?
Yeah, well, I mean, it's both. I think, and that's because I'm a realist. I think there's two distinct forms of probability out there. There's probability as it is in the world, and then there's our degree of expectations about the world. And there's a sort of that there should be a match between them. Like if we're doing well, we know about the world, we can find out what probabilities are operative in it, and then we match our own degrees of expectation to those probabilities, and then hopefully we do better. So it's kind of easy to see kind of how these two things come apart. You can come across a coin which is biased, and you know it's biased heavily towards heads or heavily towards tails. You don't know which direction it's biased in, and you think a bias in either direction is equally likely. Then the coin is very strongly biased, so the probability of it landing heads, let's say, is very high, but you don't know what the bias is, so it's reasonable for you to be 50-50 on it. So your subjective probability for whether it lands heads should be the same as for whether it lands tails, even though the kind of coin's own inherent tendency is strongly to land heads. You just don't know that yet. Of course, if you know it's strongly biased and you toss it once and you see it lands heads, then that's very strong evidence that it's biased towards heads. And so next time you'll shift your expectations strongly in the direction of heads. Whereas if you knew the coin was fair and you saw it land heads, you wouldn't really shift your expectation at all about what would happen next. So we already have, just with a biased coin, there's nothing quantum or anything in this, the apparent need to kind of keep track of two different kinds of probabilities. There's a probabilities inherent in devices like coins, and then there's our own subjective expectations about that. And the more we know about a system, generally speaking, the better we'll get to knowing what its objective probabilities are like. So a better job we'll be able to do at matching our own subjective degrees of belief to those objective probabilities. So, a gambler that knows all the odds of all the outcomes will generally outgamble someone that has no idea in poker which hands are more likely than which other hands. There's just kind of straightforward factual information about the objective probabilities out there. That, of course, hasn't stopped some philosophers trying to do without objective probabilities. So on some sorts of views, these sorts of subjectivist views of probability, objective probabilities are a sort of mirage. They are they're cases where the right way to kind of adjust one's subjective credence is rapidly, in the kind of biased coin case, or very slowly, as in the fair coin case. But that's just imagined as a personal policy for updating degrees of belief. And I frankly find it hard to take this view seriously. It's just I just find it hard to understand how it could be that the difference between kind of the probabilities involved in a biased coin is all about our subjective expectations. It's not about the coin itself. It seems to me kind of obvious that the probabilities are kind of out there in the external world. There's an objective difference between biased coins and unbiased coins, not just a difference in our expectations about them. But so that there are interpretations of quantum theory, if you know, that make probability all subjective in that way. So quantum Bayesianism, cubism, is the most kind of prominent one that's kind of very explicit that probabilities are all subjective. And I never quite have got my head around what the cubists are saying, but I think what they're saying is that probabilities are subjective because everything is subjective in physics. Like physics is about the prediction of subjective experiences, the experiences of the experimenter. It's not about an external world and what that's like at all.
Right.
And so then, if everything is subjective, including kind of all of the content of physical theory, then I suppose probabilities are going to be subjective too. But in our ordinary way of thinking about probabilities, we have this very clearly marked distinction between objective chance, as philosophers sometimes call it, and subjective credence. We use this distinction between chance, the objective thing, and credence, the degree of belief thing. Right. And then we say that credences should match chances. So there's a sort of principle of rationality. If you know a coin is fair, you should be 50-50 in how it's going to land. If you know a coin is fair but continue to insist it's definitely going to land heads, that's a sort of irrationality. Why? It's because your degrees of belief aren't linking up in the right way with the objective probabilities. That might be a mistake. It might turn out that this is all just like an illusion that there are these objective probabilities here, but it's a pretty deeply rooted illusion in our way of engaging with the world, I think.
So as you surely know that, when Bayesians, so I'm not talking about quantum Bayesians, just Bayesians, right? They start with a prior probability and they say that using, the data, you can, update your probability by something called relative entropy, something like that. There's this theorem called Allman's agreement theorem, which says that no matter what your prior probability is, if it's not 0 or 1, any rational agent will come to the same, terminal posterior probability, and probably that's what you are calling the objective probability. Do you agree with that?
Well, I mean, that's one hypothesis about where objective probabilities come from. But I think the conditions for convergence are quite idealized. I think in practice, I don't think it's going to be rational to converge. There will always be kind of the possibility, at least, of sort of conspiratorial priors that regard any evidence as kind of effectively as kind of the outcome of a conspiracy. So whenever you seem to be getting evidence for some hypothesis, that evidence is more likely to have been planted by the people doing the conspiracy. So actually, you should strengthen your degree of belief in the opposite. We see this sort of conspiratorial thinking operative in politics too. But one could have those sorts of conditional priors. Maybe those sorts of conditional priors are somehow excluded by as being irrational, but it's pretty hard, I think, to see how those sorts of convergence after exposure to evidence is going to give you all the objective probabilities you want. I mean, one thing I think that is important to notice is that, like, at least on ordinary understandings of probability, it is possible for unlikely things to happen. So, you toss a fair coin and it comes up, it is possible that it comes up heads every single time for any finite number of tosses. There's a finite probability that it will come up heads every time. And in that situation, if you saw a kind of millions of tosses long sequence all coming up heads, you would be incredibly well strongly justified in saying that it's a biased coin that's biased towards heads. But in that situation, you would in fact be wrong to do that, because it would still be a fair coin. It's just a fair coin that had landed in a very unlikely way lots of times. So what's true and what's rational to believe do seem to still come apart in these sorts of situations. And you might say, well, the probability of that happening is very low, but kind of why should we, until we've got kind of an account of why we care about objective probability on the table? That's kind of part of what's up at issue right now. So this is kind of part of what I was talking about earlier, this sort of kind of complete inability to talk around someone that simply refuses to set their degree of belief by the objective chances. They're making a mistake, but it's sort of not a rationality mistake if their priors are kind of peculiar enough. They could be rationally updating on the evidence, and yet because of what their priors are like, still end up with any posterior you like.
Well, one more question that I have about probability is that does the concept of probability make sense for events that can't be repeated? For example, if I say that there is like a 90% chance that the Labour Party will win in 2024 against the Tories, is that an objective statement? Or is there any objective probability that can I assign to that particular statement?
Yeah,
because that's an event that's going to
yes,
happen once.
Okay. Yeah, well, it's in fact going to happen once around here. If the universe is big enough, then there's a qualitatively duplicate of our world. Very likely, if you go kind of far enough, you'll find a qualitative duplicate of our world where everything happens with just the same. They even call each other by the same names in a language that sounds the same. And so if you have an infinite universe that's sufficiently rich, then there are statistics actually, even of precise situations exactly like ours, which is a kind of mind-bending prospect. But even if you didn't have that sort of kind of infinite frequency of infinite number of duplicates to kind of look at the frequencies of, I would say the many worlds interpretation, if you take probability then it seriously, is going to entail that there is a probability about that we just can't necessarily know what it is with any confidence. But there sort of has to be one there, because the political setup right now is a complicated one, but ultimately it's just a physical state. And for every, if quantum, so it's still a physical possibility. Quantum theory is still true of it. In quantum theory and the many worlds interpretation, there's, for any wave function, there's a well-defined probability measure over it given by the amplitudes. And so there really is a physical probability for the different ways in which the wave function of that universe will branch into the different possible outcomes. So probability is everywhere on these pictures. It's a kind of it's not just kind of rare, statistically well-behaved sequences that have probabilities associated. One-off events have probabilities associated. Arbitrarily complex events have probabilities associated with them. And that, to me, is just falling straight out of the universal applicability of quantum mechanics. Quantum mechanics is a probabilistic theory. So if it is the true and complete story about the universe, then every question you can ask about that universe, there's a well-defined probability over the range of possible outcomes. And that is kind of philosophically very useful. And I've kind of used that universal probability measure in my own work on the philosophy of possibility and necessity. philosophers are used to talking about possible worlds. These are the kind of complete alternative possibilities they're interested in. But philosophers have tended not to think there's any such thing as like a well-defined probability distribution over them. But if I'm right that the many worlds of quantum theory are just the possibilities that philosophers have been talking about, then we do in fact have a well-defined probability measure over them given by quantum theory. And that's, I think, quite a remarkable outcome, and is a sort of benefit of the kind of realist approach to many worlds with probabilities in it's kind of harder to make sense of a universal probability measure in classical statistical mechanics, for example, because it kind of reduces to a probability measure over initial conditions. But where did that come from? It's not itself, we don't have a sort of creation myth in classical statistical mechanics that will give us the right probability distribution kind of over the range of the whole space of initial conditions. There's no kind of story about where that probability distribution comes from. But in quantum theory, it comes straight out of the dynamics of the theory. The theory is about the probabilities.
I see. Okay, so I want to divert our discussion to another topic that you have worked on. And that discussion is about laws of physics or laws of nature in general, and what is the meaning, or what is the meaning of the laws of nature. So my question is that, are laws of nature like some entities that compel things to behave in a certain way, or are they mere regularities in a Humean sense, for example?
Yeah, so this is kind of the big kind of question which splits philosophers talking about laws of nature. Are laws of nature kind of active principles which kind of explain why things happen in an orderly way? Does kind of order occur in the universe because the laws make it occur? Or is it the other way around, that we have order in the universe, and because of that, there are good, simple, strong summaries we can make of that, and we're kind of lucky that everything turned out to be orderly. But given that everything has turned out to be orderly, now we can write down some very effective summaries of it all. And I think the reason this argument persists, obviously, is because both hypotheses kind of are compatible with the data. There's no kind of way of going to like empirically search. You can't go out and build a particle accelerator to search for a thing called a law of nature. It's sort of like a classic dividing line in the philosophical debate over laws of nature. Is it the case that we live in a universe which is orderly and predictable because there are laws or principles operative explaining why it is orderly? Or is it rather the other way around, that because we happen to live in an orderly universe, we're therefore in a position to summarize it in neat and effective ways and call those things laws? So the question from a philosophical point of view is a sort of order of explanation question. Is the universe orderly because there are laws, or are there laws because the universe is orderly, that it sort of permits those laws? So the difference is between whether laws kind of actively constrain what goes on, or whether laws are sort of passive summaries of what in fact happens. So I'm inclined towards the view there probably are some fundamental laws that probably do explain what happens. The basic argument for that is a really quite simple-minded one, that order would be surprising if there was nothing that explains why it's orderly. That there's something remarkable about the degree of structure we find in the universe, and that's not the kind of thing that happens by accident. That reasoning is very kind of is very tricky to make good on, very 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 informal. But I think that it comes down to the preference for more sort of unified total theory. total theory that says these things happen and gives an explanation for why they happen is better than one that kind of ultimately stops that these things happened and that's all there is to say. So I tend towards approaches to laws of nature which take on more of a kind of heavy duty philosophical content in order to deliver, hopefully, a more substantial explanation of the patterns we encounter in the world. But the picture of many worlds kind of changes the landscape, I think, quite a lot with respect to laws of nature. So if there are fundamental laws of nature in a many worlds quantum theory setting, presumably those fundamental laws of nature are going to be kind of laws telling us what kind of multiverse we have. There'll be laws that take a certain quantum state as an initial condition and generate the evolution of that state over time, containing within it the structure of many worlds. So there are sort of laws of the whole multiverse, which are primary to the laws of individual worlds. And those laws of the multiverse are going to be deterministic. You, given an initial quantum state, you get a given multiverse and not some other multiverse, just for definite. If that leaves open indeterminism, it's a sort of self-locating indeterminism. Where in the multiverse have I turned out to be? Could have been over there. In fact, I'm over here. Am I in a spin-up world? No, I'm in a spin-down world. And those laws, the laws that kind of characterize the individual parallel worlds in a quantum multiverse, those laws look indeterministic. So we've sort of got fundamental laws of the whole of physical reality, and then we've got effective laws which kind of apply within individual worlds. And so there's this sort of notion which I think can be made analogous to a kind of effective field theory. We have like some more fundamental field theory, but within a certain domain we have an effective theory that is a good description. In the same way, in a kind of quantum multiverse, we have the fundamental laws which explain why we have a particular multiverse. But then there are sort of effective laws that kind of apply to the individual worlds that say, here's why we live in a world that's like this and not like that. And those laws will invariably be probabilistic and indeterministic in character. They will be specifying probabilities. So the law isn't kind of, the sun will rise tomorrow. This is a kind of old-fashioned philosopher's example of a law of nature, but kind of with an extremely high, almost indiscriminable from one physical probability the sun will rise tomorrow. So all the kind of higher level laws of nature about chemistry, biology, all the sort of generalizations and laws that we use in those sciences, they will kind of be a matter of the pattern of probabilities in a pattern of physical probabilities that apply to that world.
So a lot of people use laws of nature to, I mean, I'm going to use a naive language and not be very careful about the words that I use. So a lot of people use laws of nature to say that the phenomena that we see in our universe is because laws of nature exist. And if they have to explain something, they say that, yeah, the existence of laws of nature explain this phenomenon and things like that. So, but these words are like, part of something that is like debated a lot in philosophy. Correct me if I'm wrong. So what does it mean to say that A explains B? And what does it mean to say that A causes B? What is the, can we make those notions very precise in philosophy?
Yeah. So it's difficult. Causation is something that we get our kind of closest grip on in our common experience. We all have the experience of agency, being able to kind of pick things up, move things around, change our environment, make signals to others. So we are kind of causal agents in the causal system. And so it's not at all surprising that we're quite good at thinking about causation. Nearly, all of our interaction with the world is kind of via causal interaction. So everything we do involves causation. So to do any, everything we've learned to do involves mastering causation of various kinds. It's not surprising that that is a pattern of thought that is deeply ingrained in us. It's much harder to understand forms of explanation which might be non-causal. But there are examples increasingly studied by philosophers. So explanation in geometry is sometimes given an example. You can't fit a square peg through a round hole that's not big enough for it. Why? Because the shapes don't match. Is that a causal explanation? It's not, at least obviously not a causal explanation. It's an explanation in terms of the geometry of the system. Likewise, we can give sort of topological explanations. There's the famous bridges of Königsberg example, where there's a certain set of bridges that there's no path that crosses every bridge exactly once because of the layout, the topological layout of the problem. And again, it's not that there's some sort of cause stopping you. There's no causal barrier there. It's the structure of the problem that explains why you can't. And then I've done quite a lot of thinking in recent years about grounding explanations, the kind of explanation that holds between different levels of description or explanation of reality. So I talked about chemistry and biology, the way in which chemical processes ground biological processes. The kind of biology happens because the chemistry is happening, but it's not like the chemistry causes the biological properties to change. Or an even simpler example, heat and molecular motion. What makes this cup of coffee hot? It's that the molecules around it are moving around quite fast. They've got a lot of energy. But it's not like the molecules the motion of the molecules is causing the heat by kind of bumping into the heat and like increasing the heat level by hitting it. Their collective motion is the heat or grounds the heat. And so we've got explanations there that don't seem to be cause and effect explanations, but do seem to be explanatory. Like if you want to know why the thing's hot, like how it gets to be hot, the answer is it gets to be hot by having molecules that are moving around fast. We learned how that works. We kind of achieved understanding of the system when we found out what's grounding its behavior, as well as a different kind of understanding we get from what's causing its behavior. What made it hot? Well, I put it in the microwave. I hope not. Yeah. But
sorry, but how is that not a cause and effect explanation? I don't understand.
Well, might use the word because. It's hot because the molecules are moving around fast. But just because we use the word because doesn't mean it's causal in the current sense. To give one example, it's not that it's the molecules are moving fast at an earlier time than it's hot at some later time. The time at which it's hot is the very same time at which the molecules are moving fast.
I see.
But also, it's not like in cause and effect, we expect certain things to change, like kind of energy to be transferred or something like that. But it's not like energy is being transferred from the molecules to heat. Heat just kind of is the collective motion of the molecules. It's not receiving any energy from the motion of the molecules. Okay. And so it's just not the kind of thing we kind of tend to think of as a causal interaction, the relationship between the motion of the molecules and the heat. Philosophers sometimes will say they constitute. They don't cause the heat, they constitute it. They don't sort of make it happen, they make it up. There are these various different ways of putting it. And that contrast is really disputed. Some people will say that there's really just kind of one sort of thing here. There's different kinds of it. So the kind of dependence you get in cause and effect is a different kind of flavor of the kind of dependence you get in grounding when the heat is grounded in the molecular motion. Others will say, no, there's two fundamentally different kinds of things here. Well, they seem to have a lot in common. they seem to be sort of directed relations that are associated with understanding. You understand the heat better when you know it's generated by the motion of the molecules. You understand why the window smashed better when you learn that a rock was thrown at it and like hit it. So in both cases, we gain understanding. Um, uh, but it could be a sort of just kind of a kind of resemblance between two fundamentally different things, or it could be the mark of kind of one thing in two aspects. This is a pretty kind of abstract philosophical question. Uh, some people have also tried to talk about like intermediary notions, notions that are sort of part causal and part grounding that have kind of elements of both. Geometric explanation looks like it might be have that sort of character. So there's a philosopher of physics called Antonio Vassallo, who's worked on explanation in general relativity. And he thinks that the explanations that are provided by the Einstein equations in general relativity should be understood as kind of part causal and part grounding. They're sort of somewhere in between the case of the heat and the molecular motion and the smashing of a window. The way in which general relativity explains inertial motion is sort of somewhere in between, he thinks.
I see. So we in all of this discussion we have used the word cause a lot, and that's something that people use all the time without knowing that it's a word that needs to be defined. So for example, if I have to define that A causes B, well, that definition can it come from by saying that B can be derived from A? And then there is this problem called the pole and the shadow problem, which kind of says that okay, you can't do that. But are there some other problems that come with defining that A causes B if B can be derived from A? Or is it not that simple?
Yeah. I mean, it depends what sort of thing you have in mind by derivation, whether you're talking a sort of logical derivation or whether it's a sort of physical construction
So
procedure.
so A implies B, that's what I mean.
Right. Okay. So there are lots of things that uh, seemingly imply things without being causally related to them, I think. So a starting place is that everything implies itself. We don't think that everything causes itself. Causation, we think, is a relation that holds between between distinct things. So maybe it's kind of causation is entailment between distinct things. Well, we have mutual entailments, but it's not at all obvious that there can be sort of mutual causation. Um, so kind of, yeah, every mathematical truth entails every other mathematical truth according to like classical logic. Um, but we don't think that 1 + 1 = 2 causes 2 + 2 = 4 and vice versa. So we seem to want to be kind of starting to kind of exclude certain cases of entailment sequentially from um, uh, counting as causal. I think a better version in the same vicinity might be something like this. Causal explanation is explanation where a certain kind of law of nature plays an indispensable role in the derivation. So if you have something like that, it's the case that if it were the case that A, it would be the case that B. And the reason why, if it were the case that A, it would be the case that B, is because some law of nature holds. That is the kind of scenario where we might think we should identify A and B as cause and effect. Um, that would be to kind of make cause and effect something like law mediated or law governed entailment. And that's then not so far away from some philosophical theories of cause and effect. It's complicated because even then we want to our ordinary notion of causation has quite a lot of texture that is um, uh, that seems to go beyond that. So consider um, complicated cases like causation by absence. So one that a lot of philosophers use is I don't water the plant in my office, so it runs out of water, so it dies. So what caused it to die? Well, my failure to water it. But um, Taylor Swift didn't water it either. Did her failure to water it kill it? No, because we don't think that she was in some sense responsible. But in some sense, the plant didn't care who it got the water from. So in some sense, we're in a symmetric position with respect to the watering the plant, but I count as the cause of my failure to water it counts as the cause of it dying, not Taylor Swift's failure. So there are some quite complicated kind of contextual um, factors, it seems, in the way we actually use cause and effect language. And when you go into kind of law, like the kind of context of like who counts as having caused a road traffic collision, for example, there's some quite complicated case law about under what situation somebody is or is not the cause of the accident.
I see.
And the natural thought is that a lot of those kind of notions of cause actually kind of come from what's convenient for us to have for our legal system, for like the practices of holding people responsible and charging their insurers and so on. So it's not so much that there's any kind of like deep sense of deep theory of causation going on in there, so much as like a kind of practically useful tool of a notion of causation that does the things we want for our legal purposes.
I see. So, and another way, that people use to define causation, as you surely know, is something called counterfactuals, by saying that, if A hadn't happened, then B hadn't happened. So, what are the obvious problems with that? For example, you said that, not A
Yeah,
implies not A. So you won't,
yeah,
think of something as its own cause. But
yeah.
apart
So
from that,
there are ways of trying to fix that thing. You immediately say, well, it only applies to distinct events. And there are sophisticated philosophical theories of causation of that kind. Um, I mean, one difficulty is that it's hard we don't want to use just any old counterfactuals for that, because it seems like under a lot of situations, like, if the window hadn't broken, then a rock wouldn't have been thrown at it. That seems like a sort of true counterfactual. You're kind of reasoning, well, if the window hadn't broken, well, it would have to have been that the rock didn't get thrown. But we don't want to say that the windows not breaking caused the rock not getting thrown. It's the other way around. Um, so these sorts of counterfactuals, we need to sometimes like be quite specific about which ones would be suitable for analyzing causation. And there's a sort of risk of circularity if the answer is that the ones which are useful for analyzing causation are the causal counterfactuals. Just the ones that are suited to analyzing causation. Like so we need a sort of independent way to say which counterfactuals give rise to causation and which don't. There is a well-developed approach called interventionism, which says it's intervention counterfactuals, and it gives a theory of like counterfactuals that are to do with interventions, which are a certain kind of changing of variables in causal models. And maybe that sort of theory can work. I think
I
ultimately it's
see.
not going to succeed in giving
Mhm.
a reductive account of causation. And I have to say, I'm inclined to think that just intuitively, the hunch has got to be that the explanation is going to go the other way. If you have, you know, if a stone had been thrown at the window, it would have broken. What makes that true? Well, it's the facts about the causes and effects in our world, or facts about the laws that govern those causes and effects. It feels weird to say that the facts about what causes what um, are hold because the counterfactuals do, when one could have said that these counterfactuals hold because of the facts about what sorts of things are causes and effects in our world. Um, and sometimes, if you ask why one thing depends on another, why, like, if you stopped if you don't refuel the car soon, it's going to run out of fuel and stop. Why? Well, then you start talking about the way the engine works, the mechanism of that. Those are all sorts of kind of causal facts about what sorts of causal connections there are inside the engine. So ultimately, the way we judge which counterfactuals are true, we seem to use quite a lot of causal knowledge, which suggests to me that actually the kind of, at the very least, there's a sort of mutual dependence between how we know what causes what and how we know what the counterfactuals are. It's not clear that we could have clear knowledge of which counterfactuals are true if we had no causal knowledge at all. They seem to kind of bootstrap off each other.
Sure. So there's another kind of reasoning that I want to ask you about, and I don't know if people have looked, into this kind of reasoning, because it's a bit imprecise, but let's still discuss it. So suppose that if someone asks that why B is the way it is, right? Or why something is the way it is, and the explanation that is given is that it couldn't have been any other way.
Yeah.
Like inevitability. So is that kind of an
Yeah.
explanation that philosophers have studied?
Yeah, no, this is an interesting one because it's a sort of limiting case of a few different kinds. So if I said, for example, that uh, something doesn't happen because it's impossible, um, uh, and it's impossible because of some law of nature, then that does fit into the classification that I gave earlier of like a kind of a causal explanation is one that is backed by a law of nature. It's just that in this case, the law of nature completely rules out the thing occurring. So it's sort of like kind of whatever were the case, this outcome wouldn't happen. So it's sort of like then kind of anything explains it not happening in this sort of law-governed way, because whatever was the case, it still wouldn't happen. The laws kind of see to that. So perhaps it's a sort of kind of null causal explanation, where another way of putting it would be people think of it as a non-causal explanation. They say, well, it's kind of an explanation at the level of the possibility space. It's not even, we can't ask why did the actual outcome occur instead of this other possible outcome, because there is no possible outcome of that kind. And if you think, well, why questions are always why this possibility rather than that possibility, and that thing's not even a possibility, then there just doesn't seem to kind of get a well-defined question of why did it occur at all. So that would be a way of saying that there isn't an explanation, but rather we kind of can like get rid of the desire for an explanation by pointing out it's not the kind of thing that has an explanation. And sometimes there's kind of a pretty kind of subtle distinction between explaining why something isn't the case and showing that there's no need to explain why that thing is not the case. In the first instance, we're kind of giving a positive explanation of it not being the case. In the latter, we're sort of explaining why we don't need to explain it. It's not being the case. So are we explaining it not happening, or are we explaining why there is no explanation of it not happening? Most explanations of these kinds, and it's not in fact possible, that's why it doesn't happen, kind of can be put both ways, I think. But this may be worth bringing the many worlds interpretation back in at this point, because there's an interesting distinction, I think, in the many worlds setting between things that kind of occur in some world but are just super unlikely. And here, anything that doesn't violate a conservation law is like that. So, kind of fish just being spontaneously ejected out of the ocean at enormous speed. That is extremely unlikely, but it's physically possible. It doesn't violate any conservation laws. But like the fact that we don't see it a lot, we don't really see it at all. Just like random quantum fluctuations, sending fish flying, miles into the sky. That's a sort of kind of effective law of nature, but it's basically a probabilistic thing. Whereas something that would kind of violate conservation laws, some quantum interactions that violate, I don't know, symmetries of fundamental interactions. Those sorts of things just don't happen in any world at all. There's no quantum world where fundamental symmetries are violated. And so there's a sort of so we have the kind of probabilistic kind of explanation for why this sort of thing never happens, because the probabilities are vanishingly low, versus that's not even in the probability space because there are no worlds where that happens at all explanation. So it's sort of two different ways of explaining why something doesn't happen. On the approach I liked in the many worlds, kind of the things that violate those fundamental symmetries are they just can't happen at all. It's not just that like some law of physics prevents them happening. They're not even there as possibilities. They might seem like possibilities, but in reality, it's not possible.
I see. But so you said that if it couldn't have been some other way because of some law of nature. Okay, that I understand. But what if we can show that if it couldn't be any other way, because if it was any other way, it would produce an inconsistency. So what
Right.
about that?
Right. So a lot of philosophers will think that's a kind of higher grade of impossibility altogether. But I'm interested in the view that actually that grade of impossibility, mathematical impossibility, is kind of the same grade of impossibility as fundamental physical impossibility. So I think all the real possibilities are the ones for which there is a quantum universe. And so, there are no quantum universes where fundamental symmetries are violated, in just the same way that there's no quantum universe where 1 + 1 = 3. And it's so this is a sort of this involves a sort of stronger necessity of the laws of nature. The laws of nature themselves couldn't have been different. Like quantum theory, on the picture I prefer of the many worlds interpretation, quantum theory tells us what the possibilities are for physical reality. So because it tells us what they are, it itself couldn't be different, because it holds at all of them. So quantum mechanics is, in fact, something that couldn't have been otherwise, in just the same way that mathematics. The quantum mechanics turns out, in some sense, in its content, to have more in common with the content of mathematics. It's sort of a framework in which all the possibilities live. So there are no possibilities for it to be different.
I see. Okay, so one last thing that I want to talk to you about, regarding causation before we move to another topic. I think you did talk about it, to some extent in one of your answers earlier. And the topic is that, so for example, consider trolley problem. That is a very famous problem in ethical philosophy, right? So if you are like, next to a lever that you can pull to, divert the train to a single person, apart from like, 5 people, and you don't do it.
Yeah.
Is your inaction the cause of the death of those 5 people? So what I'm trying to ask you is that, can not doing something be a cause of something?
Can not doing something be a cause of something? Well, I used this example earlier. So it is, I mean, some theories will make it hard to understand how that could be. A theory that, for example, says that causation is to do with the causation that's like to do with like physical interaction, so like physical transfer of energy. And not doing something doesn't transfer any energy. That's the point. You know, you're not doing anything. You're not transferring any energy or sending any signals. Um, and so on those sorts of theories of causation, it's just not right that not doing things can be causes. But on the view that says it's sort of kind of law of nature mediated dependency, the kind that I expressed some sympathy for earlier, there can be dependence between not doing a thing if you can identify what reasonably clearly what event that corresponds to. I mean, there's a sort of question as to kind of how to understand if I didn't do this, then dot dot dot. I mean, what are those scenarios you're talking about when you don't do this? Are they ones where you do something else instead? Or are they ones where there's a sort of gap in reality, where you just kind of cut out the thing you in fact did and don't add anything else? Or is it something like it's kind of the whole set of different ways of not doing a thing? But I think, to be honest, the probabilities are quite relevant here. So, kind of, if it's the case that the objective probability of an event occurring had I acted is high, and the objective probability of that event occurring given that I didn't act is low, then my not acting can be regarded as a cause. So there are kind of patterns of probability that would lead us to say that. There's then the question of kind of how we assess questions like, if I hadn't acted, what would have happened? Is there really an objective probability there? As I've already said, if you have quantum mechanics in the background, in some sense, we have a guarantee that there's an objective probability there. We just might not at all be able to find out what it is.
Sure.
So yeah, I think if you have a sort of set of rich enough objective probabilities in the background, then you can come up with a solid theory where absences like that can be causation.
Well, but don't you think that we should also consider the probability that I could have acted? For example, if I have a friend who is being beaten somewhere, right? If I intervene and save him, the probability that he'll be beaten is quite low. But if I don't act, the probability that he'll be beaten is quite high. But if I'm not in the same town, then
Yeah,
I cannot act in the first place. So,
right. But then then there isn't that gap in the probabilities, right? The probability of, I mean, maybe the probability that we need to consider is that, like, the probability that your friend is okay given that you try to act.
mhm,
Um, and if you're not in the same town, then even if you try, it won't actually make any difference to the probability of him being okay.
mhm,
So I think that can make if we find the kind of right, um, but this comes back to the problem earlier. Like, if I don't water the plants, I'm responsible for them dying. Someone that has no link to the plants is not obviously counted as responsible. There's a question as to whether we want to say, well, everybody really is responsible for my plant dying because they could have saved it too by watering. It's just that kind of it makes sense to talk about my responsibility, and it doesn't really make sense to talk. So we kind of leave it out the same way that when we say, uh, is there any cheese in the fridge? Is there any cheese? And the person you live with says no. They don't mean there's no cheese in the whole universe. They just mean there's no cheese in the fridge.
mhm.
So we don't talk about the cheese that is elsewhere in the universe when we understand the question and answer it. Is there any cheese?
Right.
And in the same way, maybe we just don't talk about all the other people whose absences are relevant are causes because they're not relevant causes.
Mhm,
So in that sense, like all the time, people's failure to come and intervene is the cause of everything that occurs. So like alongside, um, uh, you know, um, me pressing the button being the cause of my computer switching on in the morning,
Mm.
Uh, Other causes of my computer switching on in the morning include all the people in the world, not one by one, not coming and like smashing up my computer with a hammer.
Sure.
We just don't need to talk about those as causes because it's kind of not relevant to do so. But strictly speaking, they are causes too. It's just
Mhm.
that I'm the more like relevant, interesting, salient cause. There's
Sure.
lots of ways of trying to handle this, but absence causation is just a big puzzle. Um,
Right.
I think the truth is that our concepts of causation didn't come out of careful thought as to what concept of causation is going to work well for fundamental physics and science. It comes out of what sorts of concept of causation works well for like organizing human societies and gathering food and making plans and like organizing social relationships. Uh, there, we want a notion of causation that's going to like be usable, help us to solve problems, and contribute to kind of collective harmonious living. So it's
Hmm.
kind of not surprising that our concept of causation should be a concept which is well tuned to serving those roles and maybe gets more, um, you know, doesn't immediately like come out as the most natural concept of causation you would have if you wanted to think about fundamental physics.
So let me give you another example that I sometimes think about, and this problem is a bit, going into the ethical philosophy, but it does relate to causation. So suppose that, I'm shown a picture of a child in Africa, and I'm told that this child recently died because, we needed $50 to save him, and he died because you didn't donate to charity. So is that a cause?
Yeah. So I mean the kind of the philosopher's like unhelpful thing to say is that that depends on your theory of causation because some theories predict that they either cause that you're a cause and some theories predict that you're not. Um, Even if the theory predicts you are a cause, that theory will typically make a sort of further claims about the case. So you may, in some sense, be the less significant cause, or maybe not the primary cause, or the dominant cause, something like that. So you might still be able to have rankings of importance or significance or moral weight amongst the different causes. The same way that we often like kind of divide up responsibility um, actually, again, to come back to road traffic collisions, sometimes courts will decide that responsibility is shared. Like if both, if two drivers are both speeding in the same way and equally irresponsible, then they might be equally responsible for the action. Whereas if one
Hmm.
of them had been behaving responsibly and the other one had been behaving just the same way, they would have been fully responsible.
Hmm.
So it's sort of a relational thing that we uh, it kind of depends on what else is going on. And even if everybody is a cause, some people might be more significant causes than others. Um, and you might think that in your example, for example, the people with the most money and power are the most responsible because it would have cost them the least
I
proportionally to
see.
have helped.
I see.
Whereas the people for whom it would have been some huge personal sacrifice are not as responsible, even if in some sense they are causes too. They are they're not as morally, their responsibility is not as intense.
Hmm.
So there's a lot of ways of going that way. In terms of what my own view is, I mean, yeah, I think we probably all are responsible for all of those things, strictly speaking, and that means that we're in a sort of permanent situation of moral dilemma because there's simply no way that we can live up to all of our responsibilities. Um,
Well, so I'm sorry, go on, please.
so we have to find some way of prioritizing, and
Mhm.
all of them are going to involve some moral trade-off, some moral sacrifice, some moral imperfection. Um,
Okay, so
there may in some sense be like the best way of balancing those things off, but it's not obvious
right,
that there is any single best way.
right. So whenever we are talking about like inaction or like something that didn't happen, you're using the word responsibility. So but it seems to be the case that the word responsibility can be used when we're talking about humans. So let's take an example where human beings are not involved. For example, if I ask that why did these two balls collide, and if I give the reason that these two balls collided because a third ball didn't come and collide with the one of these two balls. Now there is no responsibility here, but is that a good cause, or is that a cause in the first place?
Yeah. So um yeah, so I think billiard balls certainly can be causes and effect. Um
Hmm.
so it's these are the relation between that kind of causation and responsibility is super interesting and complicated.
Hmm.
Um a colleague of mine, Helen Stewart, has recently been exploring a approach to these concepts whereby um, the concept of causation is an abstraction away from our experience of agency. So we understand ourselves as agents in the world. We understand ourselves as creatures that can affect and be affected. And then we sort of generalize that and we strip away the specifically agential components to give a more abstract concept. And what we're left with is a concept of causation.
Hmm.
Um, and then it may be that we still have like elements of that concept even after we stripped it down, like causes coming before their effects in time. And we can abstract further away. And then maybe we get these more abstract notions of dependence or grounding, um, or even entailment, as we were talking about earlier. But like what we're doing is taking our basic concept of agency and making it increasingly abstract. And our notions of responsibility are really tied up with agency. And as we make our notion of explanation more abstract and move it further away from agency, it's kind of probably like the associations with responsibility will reduce over time. So it's possible that like the sense in which we want to say that the brick that was thrown at the window is responsible for breaking the window, we might want to say there's a kind of a sense in which that's true, in that it was like the cause, but it's not responsible in the same way that the agent who threw it was responsible, because our notions of responsibility are fit better at the level of like agency and action than they do at the level of inanimate causation.
Hmm.
Um, so I'm inclined to I like that sort of view. Um, uh, and what that says is that we should kind of expect our theory of causation to have some kind of certain kind of curious local idiosyncratic features because it's been obtained by abstraction away from agency. And we haven't yet achieved like the full abstraction of the most kind of like natural, kind of abstract coherent notion of dependence. It will still have sort of elements that are hangovers from our notion of agency attached to it. Um, and so we're kind of inclined to continue applying responsibility talk even when it doesn't really belong there because of the way that our causal talk has roots in agency talk.
Hmm.
Um, and it may be, for example, that there's a sort of level of abstract reasoning about causation where there isn't any causation by absence, but there's a further level of reasoning about causation that's a bit closer to agency, where it does make sense to talk about causation by absence. And we can kind of use our concepts at like different levels of abstraction.
Okay. Okay, so we only have almost 20 minutes before we have to go. So I'll spend the last 15 minutes, well, 15 minutes to talk about another topic, and then we have some questions from the people. So we'll spend 5 minutes for those questions. So one topic that I want to discuss with you is the topic of emergence and reductionism.
Yeah.
So in your opinion, do you think that we have, well, first of all, what is emergence? Can you explain for the audience? And are there different kinds of emergences? And well, then I'll ask, more about that later.
Yeah. So emergence is a pretty kind of uh, shifty, messy, kind of disorganized concept. It has meant a lot of different things. Um, Emergent behavior, roughly, is behavior that is not um, uh, easily modeled at a more fundamental level, but is instead modeled um, at some more. some higher, more abstract level of reasoning about the same system. So to come back to the example I used earlier of a square peg and a round hole, if you want to explain why this peg doesn't fit through the hole, you could give a complete story of where all of the particles in the peg are and where all of the particles in the hole are, and show that there's no way of there's no like history, dynamically allowed history according to which the peg passes through the hole. Complicated physics problem, far too complicated to actually solve. But you could equally and much more better explain why the peg doesn't pass through the hole by pointing out that the peg is square with a certain diameter and certain dimensions, and the hole is circular with certain dimensions, and so there's no way of overlapping it completely. That's an explanation at the level of geometry. And it uses properties which are sort of emergent properties, the shape, the being arranged into a square or being arranged into a circle of the material constituents of the peg and the hole. So emergence is, I think, in its most general sense, the kind of phenomenon of these less fundamental properties, like being square or being round, having explanatory power that is better than the explanatory power of the more fundamental description. So anytime it's better to theorize in terms of these more abstract concepts that describe reality at a more coarse-grained level, anytime it's not just anytime it's actually better to do that, then we have emergent phenomena. And so a lot of kind of structures in the natural world are like that. Clouds are like that. We theorize better about a cloud if we theorize about it in terms of its like size and shape and mass and water content than if we theorize about it in terms of the position and location of all of the individual particles. Just a less good way of theorizing about the cloud for our purposes. And not every system would be like that. Like take a kind of completely arbitrary combination of particles in the actual universe that's like scattered throughout the universe, just kind of picked completely randomly. The system that is made of those particles doesn't have any interesting regularities or laws about it. It's not emergent. It's just a collection of fundamental facts, and that sort of system, this kind of scattered random particle system, is best theorized at the level of fundamental physics. It's only kind of rare and unusual and interesting systems that even have interesting descriptions outside the level of fundamental physics. Systems like people and clouds and pegs and holes even have certain features that kind of lend them to being understood in terms of these higher level laws. So every system described by biology or chemistry or geology or psychology or any of these higher level sciences, that will be an emergent property if the theory is a good theory.
So, as you have described, there are these emergent properties, and if you go to the fundamental level, there are fundamental laws that govern fundamental entities. So, circling back to our discussion about causation, do you think that these emergent properties are caused by the fundamental descriptions or not?
Yeah. So I think there's multiple senses of emergence. There is a sense at which organization can emerge. This is a kind of over time sense. And I think it's obvious that, like, organization can emerge over time in the sense that at the later time there aren't interesting high level structures, and at the earlier time there are. So, a few fractions of a second after the Big Bang, there are no galaxies. So, like, theorizing about that moment of the universe in terms of galaxies is pointless. Wait a few 100 million years, and it starts to become useful to theorize in terms of galaxies. And so in that sense, that structure has emerged over time. But that sort of temporal emergence, sometimes called diachronic emergence, I think is real, but it's different from synchronic emergence, which is this sort of emergence at a time, where you have, when we've got now we've got a galaxy, we still have a description in terms of the individual stars, and moreover, we have a description in terms of the individual particles in the stars. But we do better to think about the galaxy as a galaxy and use kind of well understood principles of galaxy formation to model it than we do by trying to model every single star, or especially not every individual particle in it. And that sort of way in which, you know, the galaxy right now is emergent. It's emergent because it has this distinct set of laws arising, covering it. And I think that's only a causal explanation in the most abstract possible sense of causation.
I see. So people do talk about something called strong emergence, where the laws at the higher level, like or long distances, are not derivable from fundamental laws. So what do you think about that kind of notion?
Yeah. So I mean, derivable. Why not derivable? Is it because there's actually a possibility gap? So that like these are higher level law, these are emergent laws that actually um, uh, say that some behavior is impossible, which is possible at the fundamental level. Um, uh, in which case it's simply uh, a new extra fact over and above the fundamental facts about the which emergent law we get. So you fix all the fundamental facts, you still haven't fixed the emergent facts. That sort of notion of strong emergence, I think, kind of makes conceptual sense, but is not very useful in science. Um, but like that would be that the higher level fact can't be predicted because it's just not connected to the fundamental. It just is completely independent of the fundamental facts. And so kind of guessing would, you've got nothing to go on when you make a guess as to what the higher level fact is going to be like. But I think there's other kinds of emergence which could count as strong emergence, or at least where there's some in principle reason why it's not possible to predict the emergent behavior just from the fundamental level, but it's a sort of maths and physics reason. So it's like maybe that the fundamental level does give rise to the high level behavior, but the derivation is an impossible one. Maybe to show that the fundamental level is going to give rise to a certain kind of complex behavior, you'd have to run a simulation that would require more computing power than exists in the universe or something like that. In which case, if there's a real physics reason why you can't predict the higher level behavior, or it's like a computationally intractable problem, even with infinite physical resources, it's just like kind of the, well, maybe not infinite physical resources, but like it's the kind of problem that simply is not soluble using the mathematical techniques you have available to you.
Sure.
That's an interesting fact about the system, that it can't be coherently explained and predicted at the fundamental level. And it's a real physical fact about that system. It has the kind of properties that are not predictable using certain kinds of physical processes. And that, I think, would be a kind of strong emergence, because it's the kind of nature itself that stops us building those models. Nature knows what it's going to do, but nature makes it impossible for us to know what nature is going to do. That sort of thing is a little bit like strong emergence. It's kind of unpredictable in principle, but the principles are like mathematical and physical principles. So we can have a good understanding of why we can't build models like that.
Okay, so I have two more questions before I go to people's questions, and we are running out of
Sure.
time, so let's do it quickly. So based on our discussion, where we have kind of talked about that, how it's kind of difficult to, formulate a notion of causation, and then we also talked about emergence. In the context of all of this discussion, do you think that it makes sense to say that certain entities are fundamental? Or so for example,
Yeah,
does it make sense if
well,
it's for, do we have fundamental particles, for example?
yeah, well. So, uh, I mean, I definitely think that there is like something like the fundamental theory of the world, something like the kind of true fundamental theory, which kind of uh, models of which fix all the physical facts. Whether that theory has kind of fundamental entities in it, I'm not sure. I mean, maybe if you allow fields to be entities, then maybe there are like fundamental things which are fields. Um, but I feel more confident with the idea that there's going to be some fundamental theory than that there's any fundamental things. Um, but yeah, I guess I do think there's got to be a fundamental theory. There's so much there's so much order, so much structure. I kind of feel that there's probably a reason why there's so much order, and we can trace it back, and that line of explanation will stop somewhere with a fundamental theory. It's conceptually possible that that's kind of the world is infinitely complex. So for any theory, there's a more fundamental theory behind it. But I kind of just intuitively it seems that that would give rise to more chaos than we actually see.
Mm-hmm.
So I'd be betting on a fundamental theory that's not so far away. I guess I'm a sort of epistemic optimist. I don't think it's impossible that we'll hit a fundamental theory by 2100.
There's this theory in mathematics called the Ramsey theory. It's very interesting because it tries to find regularities even when things are ultimately random. Well, even in the most random settings, there are some regularities that you can pick up on. But the number of things have to be large enough for those regularities have to be, there. Okay, so one more question that I wanted to ask you is that are there areas where you think that philosophers of physics and theoretical physicists will, it will be very fruitful for them to collaborate on those areas?
Yeah, I mean, collaboration across boundaries is in general really quite hard. And I do think that there's useful division of labor. So, in some sense, we're collaborating already by physicists doing their thing and philosophers doing their thing, thinking about what the physicists have just done. Like in the broadest sense, that is a collaboration. And it's a mostly one-way collaboration. Like philosophers of physics do more thinking about the physics that physicists have discovered than physicists do thinking about the philosophy that philosophers of physics have written about. But that's fine. Like there's no uh, that's the way it shakes out. There's no issue there. It's still like a collective collaborative enterprise.
Mm-hmm.
So I'm pretty kind of optimistic about the ability to kind of come up with a kind of a unified worldview that has elements of physics and elements of philosophy. In terms of direct collaboration, I think it's kind of unlikely that it's going to be very, very rare cases in the history of science where it's genuinely a philosophical idea that requires a breakthrough. And physicists are not bad at thinking through philosophical ideas that are directly relevant to their areas. Physicists have like worked out like a good understanding, I think, of things like the anthropic reasoning, explanations of kind of naturalness in terms of naturalness um, of parameter values. I think there's some powerful epistemology going on in those debates about, for example, naturalness in particle physics being done by the physicists. So I think at most philosophers are going to play a supporting role, kind of drawing attention to developments, pointing out problems that certain approaches still have that remain unresolved, those sorts of things. So,
Mm-hmm.
um, so I myself haven't collaborated with physicists. I've done my collaborative work with other philosophers of physics and philosophers elsewhere. Um, but I still regard myself as kind of engaged in the sort of larger collaborative operation of we're all collectively trying to understand physical reality in its different aspects. Um, if I can be useful to any physicist in what they're thinking about, that's brilliant. But I don't think I kind of need to be in order for what I do to have value as part of that larger enterprise. At least
Mm-hmm.
that's the hope.
Sure. Okay. So I have some questions from the people. So let's go through them before we run out of time. So the first question is that, well, it's a bit connected to what I just asked you. So the question is that when it comes to philosophy, the attitude among a lot of high energy physicists is not very positive. Do you think that it's based on some misconceptions about philosophy?
Yeah, well, I mean, physicists can be impatient because physics is hard and there's only so much time that one has to do it with. And so one doesn't want one's time wasted with things that don't deserve attention. And philosophers sometimes have kind of claimed to be doing things that are of important and interesting value to physicists when they may not be. And so, any kind of attention to philosophy kind of needs to be earned. Um, and I mean, I think there's a sort of practical value to setting aside philosophical questions when you can, when doing physics, but only when you can. And there are times when they come to the fore. I think anthropic reasoning in sort of multiverse scenarios and reasoning about naturalness in particle physics is, for example, one of those cases where there really are problems which are philosophical in nature that need to be addressed. I just think that physicists are smart people, and given long enough, they would work those things out for themselves. Maybe philosophers might speed things up a little here and there. Einstein credited, of course,
Hmm.
philosophy with helping him see his way through to the equations of general relativity. Um, and it's kind of hard to know what really did the work in all these sorts of situations because people kind of often kind of rewrite history a little to suit their own image afterwards. I think that happened with people that disliked philosophy as much as people that liked philosophy. So part of the kind of anti-philosophical tendencies um, in physics are certain kind of strong personalities in the 20th century that didn't have much time for the philosophers they met around them
Hmm.
and kind of made strong kind of anti-philosophical claims. Part of the deprecation of philosophy and physics also has, I think, had to do with the um, sort of Popperian falsificationist methodology that says if it can't be falsified, then it isn't of any scientific value. I think that can't be right. I mean, logic and maths can't be empirically falsified, but they're of huge value in doing science. And philosophy would be kind of broadly in that category.
Hmm.
Um, it's kind of, philosophy is kind of an important component of the total overall system of the world, but it doesn't mean that everybody needs to pay attention to it because the system of the world is a big and complicated system and we need different people working on different parts of it.
Do you think that the reputation of analytic philosophy is damaged by continental philosophy?
Well, I mean, I think they're doing different things, these
Hmm.
different forms of philosophy. I think
But people
continental
don't know that.
philosophy,
That's the thing.
in all honesty, has less to offer to philosophy of physics,
Hmm.
um, just because the ways of re reasoning about the world of analytic philosophy have more in common with those of physics, for the most part. Um, but I mean, I'm kind of pluralistic. Like we can try a lot of different things and see what turns out to be productive and constructive. We don't have to kind of ban certain ways of thinking in advance because we're worried that there'll be wastes of time. Just try it and see. And if you don't have any interest, leave it to others to try and see.
Okay, so the next question is that has your epistemic process um, ever led you to a conclusion that is controversial or unpopular? If so, what are the most controversial opinions you have and how did you get there?
That's an interesting one. I mean, I have some views which are kind of philosophically controversial. I think that all possibilities exist and are real, and that in philosophy makes me a pretty much of an extreme outlier. Um, I believe it because of believe reasons to do with the many words interpretation. Um, so that view is a kind of less of an outlier in physics, but in philosophy, it's a pretty extreme outlier. I guess my bigger picture is there's certain things to do with like what the world is like at our scale, the way that the world is like for us as we engage with it, that we just kind of can't really change our mind about. We kind of, if physics seems to be telling us that there's no such thing as humans, it's gone wrong somewhere. Probably more the interpretation of the physics than the physics itself. So there's certain sorts of things that are not going to be overthrown um, by by fundamental physics. But fundamental physics can, of course, tell us some surprising things nonetheless. It can tell us that humans um, are made of matter, which is kind of largely empty space with small, um, dense regions of mass density with large gaps between them, relatively speaking. That was a surprising discovery. Um, and so the fact that the universe used to be very hot and very empty was perhaps a surprising discovery. Very hot and with no solid matter. Um, so the fact that black holes exist is a very surprising discovery. So physics can overturn things, but it's not going to overturn anything too close to home. So it's not going to overturn our basic worldview. It might overturn what we take to be the kind of theoretical underpinnings for that basic worldview. Um, but I'm fairly conservative. I think kind of philosophy done well leaves most of our assumptions as they are.
Okay, so the next question is that are there any book recommendations or practices what could engage in and you would recommend for getting good at thinking rigorously?
For thinking rigorously about the intersection of physics and philosophy, or
It doesn't say. It's a very open-ended question, I would say.
yeah, I mean, I'll interpret that about in the kind of areas that I think about. So,
Hmm.
um, on the many worlds interpretation, it's hard to look past David Wallace's book, The Emergent
Hmm.
Multiverse. It's just a fantastic book. Um, you were asking about the relation between grounding and causation, or causal and non-causal explanation, quite a lot. Um, a couple of interesting books on this are Making Things Up by Karen Bennett, which is about the philosophy of dependence, and Because Without Cause by Mark Lang, which is more to do with philosophy of maths, explanation in mathematics and logic, those sorts of things. Um,
Okay.
I mean, there's many good books I'd recommend. I might also mention Janan Ishmael, um, who has written a nice book called How Physics Makes Us Free, which is a kind of relatively accessible, kind of popular book on philosophy of physics and how it interacts with kind of human concerns like freedom and um, uh, the future.
Okay, so the next question is that can you think of any other way we could have discovered the possibility of many worlds interpretation with the same current trigger other than through quantum mechanics? Okay.
Yeah, so I mean, I think the many worlds interpretation, as I know about it, as I understand it, is quantum through and through. So it kind of wouldn't be the many worlds interpretation if it wasn't quantum mechanics. I mean, people had come up with many worlds hypotheses that aren't quantum before. Um, and in some sense, they were right. I mean, the idea that there were multiple planets like ours was at one time a sort of many worlds hypothesis, and we now think it's just straightforwardly true. Um, at one stage, the idea there might be more continents than just the continent you grew up on was a sort of many worlds hypothesis that turned out to be true. So many worlds interpretations have kind of come up in the history of science a lot, in the sense that our universe has been getting bigger. So we've gone from thinking that there's just one continent to thinking there's just one planet, to thinking that there's just one galaxy, to thinking that there's just one universe. And the thought that there are many universes is kind of, in some sense, of the kind of logical next step there. The difference, of course, is that all of the different um, planets we take there to be are part of one space time with one causal story, one sort of kind of causal history of the whole lot. Whereas the different worlds of the many worlds interpretation are causally isolated. And I'm not sure we could ever have had reason to believe in causally isolated worlds with something like quantum theory that gives us a mechanism for explanation of one in terms of the other. We have quantum interference. If it wasn't for quantum interference, I'm not sure there would have been good reason to believe in causally isolated worlds.
Okay. Now this is a question which is very open-ended, but let me ask it anyway. So the question is that is it correct to allow finiteness with respect to the universe?
Yeah, so I'm interested in this question. I don't know the answer, obviously. I think it's an open question in physics. I think finiteness hypotheses should be considered because kind of the assumption of infinity is it's kind of often in a sense sometimes the finiteness assumptions are for modeling modeling reasons, like they make for better models. Sometimes finite models make for better models, sometimes infinite models make for better models. And so we've got to be careful not to kind of project what models it's easy to make onto what reality is like. Um, but I think there's something quite attractive about the idea that the possibility space of the universe might be finite. Like ultimately, there might be finitely many worlds.
Mhm.
Um, that would require kind of the information content of the universe to be finite. Um, but it is, and that is the kind of thing that might, in principle, I think, come out of a future version of string theory or a future kind of successor theory of quantum gravity. So we should be open to that hypothesis. It makes certain philosophical problems easier if the universe is finite, but that's not a reason to believe it. I think that would be wishful thinking if we thought that we should believe in finiteness because it would make our life easier. Um,
Okay.
but it's definitely an open possibility to be treated as
So
such.
so this is the last question. The question says that can a solipsist worldview mean everything we know about physics might not be fundamental? Is there anything we can learn from solipsism, or is it just an
Yeah,
unproductive
I mean,
pathway?
solipsism is philosophically interesting, but I don't think it kind of, I don't think it's something to take seriously as a hypothesis about what the world is like.
Mhm.
Um, I mean, the best in my, I mean, some people are panpsychists, think that the reality is conscious, and they think that partly because they think the hard problem of consciousness is really hard to solve. You can't explain in principle how you get consciousness out of matter. I don't think that it's in principle impossible to solve. So I'm not motivated by that sort of line of thought. Um, and if you think that kind of minds are just another thing that's turned up in the physical world, um, then you're going. It kind of would be odd to make them fundamental to physics. So views of physics that build the observing mind in at a fundamental level, like kind of consciousness causes collapse kind of views, for example, or even cubists that make consciousness fundamental, that make subjectivity a fundamental part of physics. It seems to me that that's looking for the fundamental in the wrong place. Um, but if you were so convinced that the mind couldn't possibly be reduced to anything material, that the mind had to be fundamental, then it would seem to you to be the right place to look. Um, and I think we should explore both options. But I myself don't find that the sort of idealism or solipsism a very plausible part of an overall picture of reality.
Sorry, there's one more question. The question is that what do you think happens to a person's consciousness when branching happens in the many worlds?
Yeah. So if you think that worlds split, so one world becomes two, then you have to think that under normal circumstances, one consciousness becomes two.
Mhm.
And that's very hard to understand. But um, uh, you might think that such a thing could already be possible even within our world, in like a sort of split brain sort of hypothesis. Suppose that we got so good at brain technology that we could kind of split a person's brain down the middle and maintain consciousness active in each side separately. Sooner or later, there would have to have been a move from unity of consciousness to split consciousness during that. So maybe roughly the same sort of thing happens in those two situations. I don't really like that way of thinking about it. My own preference is for a more parallel worldview. So there were two consciousnesses all along. It's just from the inside they were indistinguishable. So on that sort of view, the number of consciousnesses doesn't rise over time under normal circumstances, nor does the number of worlds. We just steadily learn more about which world we're in.
I see. I see. Do you want to say that, the many worlds interpretation may be the same as the parallel worlds found in, for example, like multiverse, for example, or are they different?
Yeah, so not the same as in the inflationary multiverse, but the same as in the parallel worlds that philosophers have talked about when they use the phrase modal realism. So David
Okay, I see.
Lewis is a defender of modal realism in philosophy. He says there are parallel worlds. he says that for philosophical reasons. For him, they're all separate in separate spaces and times. And I think that model works quite well for the many worlds interpretation, honestly. I think maybe, the parallel world metaphor just avoids a lot of the problems that the splitting world metaphor generates. Questions like kind of what happens to mass conservation when the world splits?
Yeah.
What happens to probability when the world splits? What happens to us when the world splits? If the world never splits, then those problems become obviously easier to address.
I see. Okay, so I think I'm done with my questions. Thank you so much for your time. It was great to talk to you.
No problem. Really interesting questions. Thank you, everybody, and thank you especially, Hassan. Enjoyed talking to you.
My pleasure. Thank you. So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.